Welcome to problem solving session for computational commutative algebra. I'm Siddhi Balwamburi from IT Gandhinagar, and today we will discuss problems related to Nullstellensatz, Buchberger algorithm, monomial basis, elimination, and some topics related to modules. So we will start with our first question. If you have any doubts, please unmute yourself and you can ask in between. Let fg in kx be polynomials of positive degree where of course k is filled. Okay, k is an algebraically closed field, and suppose this ideal f comma gy minus 1 of k x comma y. So now we have this. So f and g are from kx. So f and g are from kx, the polynomial in one variable x. But now we have this y term here. So now this entire ideals become ideal of kxy. And we assume that suppose this ideal contains 1. Okay, 1. So we have to pick the correct option. From below. And options are first that every irreducible factor of f is an irreducible factor of g. So they are asking, so f and g are polynomials in kx. Okay, kx is PID, and it has we can factorize a polynomial here in irreducible terms. So they are saying that irreducible terms of f, irreducible factors of f divides irreducible factors of g. So every irreducible factor of f is an irreducible factor of g. G might have some extra irreducible factors, but they say that irreducible factors of f are at least there in the at least forms irreducible factors of g. And the second question and second option is that g has an irreducible factor that is not a factor of f. So they are saying that g has one irreducible factor which is not a factor of f. Factor of f. And last option is that f has an irreducible factor that is not a factor of g. So this is another option. And D, they are saying is none of the above, none of this holds. And we can still have some ideal of the form f comma gy containing 1. Okay, so any cases for this? So this is the question, and okay, so we want this ideal to contain 1. Okay, so this is something contain 1. Okay, so we want this ideal f comma gy. So we want f and g such that f comma gy minus 1 contains 1, and we want to see what properties f and g must satisfy to have this condition hold. Okay, so we will try to see that they are saying of f and g are of positive degree, so f and g are not some constant elements. Okay, so we want such kind of elements. I mean, we can put just here 1 and 1 in case in place of 1, so you can't have this kind of ideal. Okay, that then it is y minus 1. They want this x, f and g to be some positive degree polynomial. It contains at least one variable as its term. Okay. Oh, so if I take f to be x and g to be x, then what will be this ideal? F is equal to g is equal to x. Then this ideal becomes x comma xy minus 1. And does this ideal contain 1? Yes, right, because I can multiply this first term by x and minus this xy minus 1, and I will get 1. So in this case, this is f and this is g, and factor of f is also a factor of g in this case. Okay, so we want such kind of condition. So you can find examples where these two condition does not hold. Okay, so we will try to prove this first theorem. I mean first statement in this case. Okay, we will try to prove. So proof of 1. Okay, so we first observe that note that since 1 belongs to f comma gy minus 1, which it's contained in kx, it is enough to consider f to be an irreducible element. Okay, because since fi divides f, this implies that f is some h into fi, right? So instead of writing this, so 1 is in here, so 1 is some pf plus q into qy minus 1, right? So instead of that, I can just take this to be p dash into fi plus this q into gy minus 1, where this p dash is some h into p. Okay, so I hope this is clear that instead, so for example, if f is some f1, f2, up to fm, so instead of taking all this, we can merge them as a coefficient, which when we multiply to fi gives us this equation. So we can just, instead of taking f as a product of irreducibles, we can just work with f to be a irreducible element itself. Okay, if you have any doubt, please ask. And so therefore we work with f comma gy minus 1, where with f as irreducible element. Kx. Okay, so since kx is PID and, and f is irreducible, so when I say PID, I mean principal ideal domain. It means every ideal in Kx is generated by a single element. Okay, so this implies this kx mod f is a field. Okay, because this is irreducible element, so since in kx the ideals generated by irreducible elements are maximal. F is irreducible. Okay, so let us rename this and let us call this field to be L denote. We are just, so this is field because this F is maximal ideals. So this kx mod F must be isomorphic to some field. Okay, and so since this is kx quotiented by F, so this x must be some alpha. Okay, so if I take this map kx to kx mod F, okay, so x goes to some element here, right? So it is x bar. So let us call that element to be alpha for now. Okay, so let alpha be an image, the image of x in L. Okay, so now note that this kxy, which we are starting with, quotiented by this f gy minus 1. Okay, we want this to contain 1. Okay, so we will try to see how the quotients work with it. And since we have this information that quotient when we take with respect to f, we get filled. So we will try to work with quotients. And this is now isomorphic to k x comma y quotiented by f or let me just write this for now. Quotiented by kx quotiented by f, kx quotiented by f, this whole ring y quotient by g tilde y minus 1, where this g tilde is image of g in kx mod f, because this g belongs to kx. Okay, if you notice this f, so this f comma gy, the ideal is in kxy, but this f and g are elements from kx. Okay, so under this map, let us call this map pi. This g tilde is the image of g under this map pi when we take kx goes to kx mod f. Okay, and how we get this? Understand that this is kx comma y quotiented by fg minus y. Okay, so this is isomorphic to kx comma y quotiented by f quotiented by this f comma gy minus 1 quotiented by f. Okay, this is kind of third isomorphism theorem of ring homomorphisms. You can do this. You can see the statement. So it is like when, because we can do this because this ideal which we are taking now quotient is contains this ideal. So since f is contained in f comma gy minus 1. Okay, so the statement is something like this. If I have k mod I, then this is isomorphic to k mod j comma I mod j. But in this case, I need to have j contained in I. Okay, then this hold. Okay, so we have this terms here. Okay, and now see what this, I mean, top of the quotient, I mean, this ring here looks like. It is k x comma y quotiented by f, right? So what is this? This is some h plus f, elements of this ring, where h belongs to kxy, right? But then I can write this h as polynomial in y. Okay, so every polynomial, so h is in kxy. So I can just write it in the polynomials of y. So let me just write it like this. So it is some Pn of x, y power n, plus Pn minus 1 of x, y power n minus 1, so on up to some P naught x, such that this Pi's belongs to kx. You can write this, right? For example, if I take this polynomial x square y cube plus 7x y power 7 x square, whatever you want, and x cube y cube plus 7x. If I take this, then I can definitely write this at 7x square. This is some polynomial in x power 7 plus this x cube plus x square into y cube plus 7x. So this is my kind of P7x. This is my P3x. And this is my P naught x. So I'm kind of considering polynomials in x as a coefficient so I'm considering this as this kx as kx y. Okay. So I'm now considering it as polynomials in variable y with the coefficients from kx. Okay. So then this term here, so this kx comma y quotiented by f. Oh, here it must be some, not some, f plus where this pi is in kx. Okay, we are working with these elements here. Pi in kx. Okay, so when I take quotient, note that this f is in kx. So when I take quotient, it only affects this p naught x and it doesn't affect y. So it becomes now what? Pn tilde x y power n plus Pn minus 1 tilde x y power n minus 1, so on up to P naught x tilde, such that this Pi tilde x belongs to this field Kx mod f. Okay, this is my field L, which I had defined. So this becomes what? This is what? This is Kx quotiented by f into y. Okay, that's why we wrote here. If I mark this as some star, that's what I had written here in the top part. And in the denominator, not the denominator, but when we are taking the quotient by this g tilde y, it is this term right here. So when I do this g has some image under this quotient. So we are taking that. So the entire thing becomes this k xy quotiented by f comma gy minus 1. This we got that it is isomorphic to kx mod f. Okay, and y quotiented by this f is gone now. F is a 0 in quotient f. Okay, so this is just g tilde y minus f. Okay, so and we already gave notation to this field. So let us write it in that form. So it is ly quotiented by g tilde y minus 1. Okay. Any doubts so far? If you have any doubts, please let me know. You can also write it in the chat if there are any doubts. So if, yeah, clear. Okay, great. If I know this is lengthy and has many things going on, but we have to go through all this. So if alpha is image of this x in L, then this g tilde is actually equivalent to this g alpha, right? Like that's how things are, because x is going to alpha. So any polynomial in x goes to that polynomial evaluated at alpha. Okay, that's how that is because of the properties of ring maps. Okay, so as we have that 1 belongs to f comma g y minus 1, because that's how we chose our f and g to be, our 1 belonging to that ideal. So this implies, since this everything is an isomorphism, this 1 must belong to this ideal as well. So this implies this 1 also belongs to g tilde y minus 1. Okay, so this one and this one are kind of different one, though they are like multiplicative identity, this in this ring and in this ring and so on. Okay, so 1 belongs here. So these imply what? That this g tilde y minus 1. So note that this ly is again a principal ideal domain. I hope you get that, because this L is a field and this is filled with one variable. So it is again, so when 1 belongs to this thing, this element becomes unit, okay, is a unit in Ly. Okay, and this is the result which is well known, and it is also like exercise of first chapter of Atia MacDonald book, Introduction to Commutative Algebra. And it says that polynomial, in a polynomial ring, a polynomial is a polynomial, let us say it has this form, x1x plus an x power n, is invertible if and only if just a naught is a unit, and all these ai's, a1 to an, are nilpotent. Okay, so when I have this g tilde minus 1 is unit, g tilde y minus 1 unit in Ly, which is my polynomial ring, this implies what? That 1 is unit, that is okay, that is there, and this g tilde is nilpotent. But once I have some element nilpotent in a field, this implies that element is 0, right? Because we are in the field, we are in an integral domain. So we can see if this g tilde n is 0, this implies this g tilde is 0, right? Since L is filled. So once I have this g tilde 0, this implies this g belongs to f. This implies f divides g. So these imply that irreducible element or factor of f is irreducible factor of g, because that's how we can say that f divides g. Okay, any doubts here? This is good exercise, you can try. Okay, and it actually immediately follows from this simple thing, that if u is unit and a is nilpotent, then u plus a is unit. Okay, it follows from this. So when you take this element and consider its inverse sum b naught to b m power xm, and when you try to compare them coefficient wise, you can easily prove this. Okay, this you can check, and using this we get that since f divides g, we get that the irreducible factor of g must be a irreducible factor of f. Any doubts here? And that's what the first option was, that every irreducible factor of f is an irreducible factor of g. No doubt. Okay, great. Okay, so we will now move ahead, and yes. Uh, we will try to do this question. that what is the kernel of the ring map kxy to kt power a comma t power b in kt. So this is considered as subring. That's not a problem. This is also image. I mean, this is, if we consider this map from here to here, this is a surjective map. So sending f of xy is now goes to f of course, t power a, t power b. Okay. And these are our options, that it is, they are saying that kernel is x power a minus y power b. I am choosing this. X power a minus y power b. Second is x power b minus y power a. Third one is x power b minus y power a, comma y power a. I mean, the ideal generated by these two terms. And last one is none of the above. Oh, it's not AB. It's 2 and 4. Oh, not here AB and none of the above. So, any guesses here? What will be the answer? So, if we consider this, I mean, for any given AB are belong to Z plus. These are positive integers. So, can you guess, like when we can say this, that this will always follow, or this is kernel, or this is kernel, or this is, or any of the kernel? I mean, can we fix something that, okay, at least this will be the kernel for the map and so on? Can you choose A and B for which any of this is kernel or not, something like that? So let us start with the at least first map. Let us take this kx comma y going to k t power 3 t power 4. Okay, simply anything, any integer we want. So here they are saying x minus a y power b. Okay, so x power a means what? That t cube. So f of, if I take this x comma y, f of x power a minus y power b. This is what? T power 3 minus t power 4 power 4. And what this is? What is this? This is t power 9 minus t power 16, right? And this is definitely not 0. So therefore this x power a minus y power b doesn't belong to kernel of this map. Let us call this map phi. Okay, so first one is definitely not an answer. Okay, and second one they are saying x power b. Okay, okay, x power b minus y power a. This one you are saying x power b comma y power a. Let us check that also for the same x power b f of. So when we say that if this x power b my comma y power a is like kernel of this map, kernel of phi, then this implies what? X power b belongs to kernel of phi and y power a belongs to kernel of phi. But if I take f of this x power b, what it is? T for this a and b, for this particular phi map, it is t cube power 4, which is what? T power 12. And this is not 0. And similarly, the f y power a, which is t power 4, power 3 is again t12, which is again not 0. So C is also not the option. I hope you understand why this is not the case. I mean, none of them, like the individual monomials, individual these pure powers here are not giving us 0. And now let us try to find this B. Check for the B. Okay. Yes, I mean, these are like individual elements. I mean, the combinations of x power b and y power a definitely might give us some elements which belongs to kernel. But they individual, I mean, if when we are saying that they are equal to the kernel, the generator itself must vanish under that map. Okay. So that's not happening, at least for the C part. Now let us check for the B part. Okay. So what is B? It is ideal generated by x power b. So this is not true. So this is not true. Okay. So what we are saying now that kernel of B is x power what? B minus x power y power a. And now let us check for this. Okay. So for this map itself, let us try to find that f of x power b minus y power a. It is what? It is t power 3 power 4 minus t power 4 power 3. And what this is? This is giving me 0. This is both t power 12, t power 12. And this is definitely giving me 0. So, but what this implies? This implies that this element x power b minus y power a contains kernel phi. Okay. But does this exactly equal to that element? Okay. Can you say what is like, can we talk about the equality? Any guesses, like, will this always be equal for any chosen map P for any given a and b positive integers? Okay, so that's not true actually in general. For example, if I take this map P from kx comma y to t square comma t power 4. Okay, so how this is f of x comma y contains in kt, that's not a problem. F of t square minus f of t power 4. Oh, not minus, comma. Okay, so can you find some element which like vanishes? And so as per the guess, they are saying that from this we already have that x power 4 minus y power 2 contains in kernel of this map phi. But if kernel phi is equal to this x power 4 minus y2, that is the question. So can you give an example of a polynomial which uh, vanishes under map P, but is not element of this ideal here? Uh, can you give one such? We have this t square and t power 4. So clearly this t square minus t power 4 is 0 here, right? But if I want to see this, it is what? This is what? F of x square minus y, right? So these imply what? That x square minus y belongs to kernel of phi. But clearly x power x square, sorry, x power 4 minus y square doesn't belong to this, doesn't divide this element x square minus y. This is clear, right? That this element doesn't belong here. Therefore, this x square minus y doesn't belong to this ideal, this principal ideal generated by x power 4 minus y square. So therefore, kernel of P is definitely not equal to this x power 4 y square, which was this x power b minus y power a in our case. This is definitely holds always that this belongs to kernel. Okay, but equality is not guaranteed. Okay, so even this is not true. So answer is none of the above in this case. Okay. So this B part actually holds when GCD of A and B is 1. Okay, you can check this. Okay, in that case, this happens. Okay, so for now, none of these three ideals which are given here gives us the kernel of this map. Okay. Okay. Any doubts? Okay. So let us see kernel of this map in Macaulay 2 once, so that we can see how for different A and B the kernel looks like for this map. Okay, we will define few maps. Just let me share the screen. Okay, so I hope you can see the screen. And let me define this map as, let me define first polynomial ring, xy, x comma y. Okay. I hope this, let me just zoom out a bit. Okay, x comma y. And then t, I define this one variable ring, ut. Then my map f, let me call it f1 for now because we will see kernel of multiple maps. Map from S to T. So in Macaulay 2, when we give map from S to T, we write it like this. It is from first we enter T, then S to define the map. And where the first, so, and this in this bracket, the first entry we choose is like we are sending X to that element. Okay, so where my X is going, so in our case, it was going to T square and Y was going to T power 4. Okay, so this is the map defined. And now let us check what is kernel of this F1. It is x square minus y, if you can see. But now I change this to 3 and 4, where GCD of this two A and B is 1. Oh, okay, it doesn't matter. And now the kernel is x power 4 minus y cube, which I said like that the second idea, the option 2, which in our case, x power b minus y power a. That's exactly how. Let us do that for one more map here. Instead of 4, let me just put here 7 and here 9. Doesn't matter. Okay. And now kernel of this f2 is again y power b minus x power a. Okay, it just shifts as per the powers. So x power a minus y power b, y power 9 minus x power a. That doesn't matter. But ultimately it is, so we are in filled and also this is like minus of that element. So if f generates something, minus f also generates that same ideal. So that's not a problem here. So since this is considered, so qxy when I write, it works in graded reverse lexicographic order, that is degree reverse lexicographic order. So when we define a polynomial ring in Macaulay 2, by default it considered it as a polynomial ring with the graded reverse lexicographic order. So that's why it gives us outcome of the polynomial in with the initial term first and so on. Okay, the decreasing order of the terms. And now let us again, just to be sure that this doesn't always hold, let us try to do this with 9 and then 27 and see how this works. Kernel of F2. Now again, it's not x power b minus y power a. Okay, in this case again, this 9 is say 27 is 3 times 9. So here I have x cube minus y. Okay, and so on. So you can work with this and see that what exactly, I mean, you can you give formula for this x power b and y power a depending on the GCD of a and b and so on. Okay, this is a good exercise. Please try for yourself. Okay, and then we will go back to our writing screen, and I hope you can see my screen. If you have any doubts how map was defined and everything, please let me know. Otherwise, I will proceed with this. And now we will see, like, okay, great. We will now move to next question. This is, I think, question 3 for us. Yeah, question 3. So they are saying, find the remainder when x1 square plus x2 x3 plus x4 square is divided by x1 plus 1 in lexicographic order. Okay, so we have to find this in lexicographic order. So since this is something different, so this is not our normal division algorithm which we have studied in our schools maybe. This is now we are working in polynomial division and in multivariables. So let us see quickly the definition for multivariable. And before going to multivariable polynomial division, let us quickly just go through the definition for single variable also, algorithm for polynomials. Okay. For one variable, okay, so k is filled and r is this kx, and f and g are in r and g is non-zero, of course. Then we say that there exists q and r in r such that this f is qg plus r, where r is either 0 or degree of r is less than degree of this element g here, by which we are dividing the polynomial f. Okay, so saying this is equivalent to say that this, saying this is, let me just write here, is this at least is equivalent to say that this r is 0 or initial term of g is not divided by any term of any term of r. Okay, so initial term of g is not divisible by any term, any term of r does not divide g, and so on. Okay, so this is anyway, the definition is anyway given in the book. And for multivariable polynomials, so let me type, it is written as the multivariable case. It is given as a theorem in the book, in our notes. So I am writing it as a theorem. So they are saying that let r is equal to k x1 to xn and be some monomial, so greater than be some. So order we define denote by this greater than symbol, monomial ladder, and f comma g1 to gm are in R now, and then there exists a1 to am in R and this R in R such that again I can write this f. So this is not only multivariable division, this is also we are dividing it with respect to multiple polynomials. Okay, so there's difference when we divide it by just one element and multiple elements. So if we only consider g1, it is for g1 only, it will be some a1 g1 plus r with r satisfying some condition, but we are doing this something more general in this case. Okay, where now again there are some conditions of r where r is 0, or they are saying r is such that no term of r is divisible by initial term of gi for all gi. Okay, no initial term, I mean for all gi's, their initial terms does not divide the any term of r. Okay, when I say this any term of r, we will see this. We are now working with lexicographic order. Okay, we are given lexicographic order. This is not graded lexicographic order. This is just lexicographic order. I mean, in graded reverse lexicographic order, x1 is less than x square. Okay, but in lexicographic order, so let me write g lex. But in just lexicographic order, x1 is greater than x square. Okay, so there is a difference. Okay, and why this any term here? Okay, why this any term? No term, I mean, no term of r is divisible by any gi. We will see like why that no term is important and not just the initial term of ri. Okay, so our polynomial is x1 square, x2, x3 plus x4 square. Okay, I have arranged it in decreasing order of lexicographic. I mean the terms I have arranged in decreasing order of lexicographic order. And again, I'm dividing by this polynomial. So it is x1 into x1 square plus x1. Okay, and then it is x1 minus x1 plus x2, x3 plus x4 square. Okay, and now this x1 is again has, I mean this x1 can still divide this x1, and we will get minus of 1 and minus x1 plus x1, sorry, plus 1, not plus 1, I minus 1, and I get x2, x3 plus x4 square plus 1. Okay, so why that no term is, because if this was graded graded lexicographic order, then this polynomial can be written as like this: x4 x2 x3 plus x4 square plus x1, right? This will be the smallest term in that case. And if we only had here that initial term of r is not dividing initial term of g and so on, I mean the other way around as well, whatever suits, then we would have got this as our reminder. But that's not the case. This is our reminder here with 1 here instead of that x1. Okay, so that's why no term of r is divisible by, oh, I wrote it in the, no term of r is divisible by gi. Okay, I hope this is clear. If you have any doubt, please let me know. I mean, when we do this, we have to check whatever polynomial here is, no term must be divisible by this initial term of the divisor. Okay, any doubts? I don't think this is just division. And in Macaulay too, I did this last time also. Okay, here. So still, we will try to see the what I was saying. We will try to see this division again here in Macaulay too. Okay, and now let me clear everything. Because my this yeah, it's clear. Okay, so when we do clear all, it clears all the memory. So here my x was some variable and f1 was this map. But when I cleared everything and wrote this f1, for it, it was just a symbol because now it does not have any memory stored for the variable f1. Okay, so when you work with many rings in one go, it's clear to like not to mix up the rings. Write just clear all and try to write your entire code again. So my polynomial ring is x, yeah, 4 variables. So let R be q x1 to x4. Okay, if you want, you can give monomial order since they said that they want monomial order to be lexicographic order. Let us define this f to be x1 square plus x2 x3 plus x4 square. Okay, this is the polynomial f and my g is just x1 plus 1. And when I do this, f%g is the symbol to find the remainder of this f when divided by g. And this is exactly the polynomial which we got. Okay, and this actually does not depend on order we choose, because if I do this and again I define f under, now this when I do this is under, or let me just do this so that you can see the difference. And when now I am defining this ring S here, and when I again write this polynomial f here, it now considers it as polynomial from ring S instead of polynomial from ring R. So the latest ring you define, unless it has different order, different variables. For example, I had defined earlier a ring, for example, say t with variable t, and if I somewhere write monomial with the variable t, it understands that monomial or polynomial is from that ring. T is equal to q t maybe. Okay, but if there are multiple rings with the same variable I have defined, for example, here the ring R had same variable x1 to x4, and S also has same variables x1 to x4. They have different, I mean, it doesn't matter if they had different order and so on. The Macaulay 2 considered the polynomial f as a polynomial of the ring which was defined the latest. For example, it considered this f as a polynomial from ring S. Okay, and again I define this G. Okay, and now f divided by G is again the same polynomial here. Where is it? Yeah, x2, x3, x4 power 2 plus 1 and so on. Okay, so any doubts for now? So I just wanted to show that you can also use Macaulay 2 to find the remainder of a polynomial. Okay, let me go back to the screen. Okay, so this was our question. And now the S polynomial, which I mentioned in the last lecture for Buchberger algorithm. let us do one question related to that. What is S polynomial or S pair, and so on. So let us see what is it. So what is S f comma g? That is S pair of polynomial f comma g, where f is this polynomial x1 square plus x2 x3 plus x3 square, and g is now x1 x2 plus 1 in k x1 to x3 under with graded reverse lexicographic order. When I say this, I mean it is degree reverse lexicographic order. I hope you still remember the definition of graded reverse lexicographic order. If not, please let me know. I will recall it. And for now, I'm defining what is this S pair. So if R is polynomial ring x1 to xn, K is filled again with fixed monomial order. So we take this polynomial f and g in R, and both of them non-zero. Oops. Then the S pair, or also known as S polynomial, of f and g is this SF. It denoted by this f as SF comma g, and it is LCM of initial term of f comma initial term of g under this monomial order, of course, into f, and everything divided by now initial term of f. And this is well defined, and this is in polynomial ring, because see, here we have LCM of f, initial f and initial term of f and initial term of g, and then we are dividing it by initial term of f. So this LCM always, for example, LCM of AB, A always divides LCM of AB, and B also divides LCM of AB. So that's why this is well defined into f minus, again, let me write here, LCM of initial term of again f, initial term of g, divided by initial term of g into g. Okay, and this is subtraction. So this term minus this term. This is my S polynomial. Okay, and we have to find S polynomial for these two. So let me just copy this. This is my f, and this is my g, and I have to find S polynomial of this. So S polynomial of this f comma g is LCM of initial of f is what? Here we are in graded reverse lexicographic order. So anyway, x1 square is greater than x2 x3. Okay, so the smallest, so last time if you remember, we kind of, so in case of lexicographic, graded reverse lexicographic order, if degree is equal, or the first entry of a minus b, or first entry of a the monomial or variable with the least index must have highest power for it to be bigger. But in case of graded reverse lexicographic order, the variable with the highest subscript or highest index must have lowest power. Okay, so LCM of this, so I hope you know that you can verify now. We did this multiple times, that these two are initial terms of this. So this is x1 square, comma x1, x2. We will also check this in Macaulay too, how things are. But for now, we will do it by hand. And initial f, that is leading term of f, is this into f. Okay, minus now again f, I'm not writing again for now. This is LCM of x1 square comma x2. Now initial term is x1 x2 of g into g, and this is the LCM of this is x1 square x2 x by x1 square into f. I'm now writing explicitly x1 square plus x2 x3 plus x3 square minus here again it is x1 square x2 x1 x2 into x1 x2 plus 1. Yeah. So this is what x1 square get cancelled and it is x1 square x2 plus x2 square x3 plus x2 x3 square minus now here I get x1 x2 x1 square x2 plus x1 x2. No, only x1. Yeah, here it is this term is x1 and here this term is x2. Okay. So I get this and this first terms get cancelled and I am left with this x2 square x3 plus x2 x3 square minus x1. Okay. So under graded reverse lexicographic order, this is the S pair. Any doubts here? This was simple calculation because polynomials were not that difficult. And I mean, thus 3-term and 2-term polynomials. So any doubts here? Okay. Now let us try to find this S terms in Macaulay 2. How to do that? Okay. Let me share this screen. You can quickly do this because if you want to do some calculation by hand, you must be able to, like, you should be able to find those. Just a second. Which screen? Let me share the screen for now. Yeah. Share this. Yeah. So I hope my screen is visible. This. Yeah. Oh. And we'll now define this polynomial ring QQ x1 to x, I think 4 variables, 3 variables, doesn't matter. And now this S polynomial is f is equal to my x1. Let me just check. Yeah, x1 square plus x2. I'm not explicitly writing the monomial order of S because in Macaulay 2, by default, it considers x1 x2 plus 1. Order to be graded reverse lexicographic order. Okay. So that's not a problem in our case. So S polynomial S pair is what? LCM of, let us put bracket first, LCM of lead term of F. Okay. So LCM of lead term of F, comma, lead term of G. This whole thing, this LCM, now divided by lead term of, I hope we don't end up getting any star F. Okay. Minus this LCM of same. This part from here to, I guess, here is similar. I mean, the entire term is similar, except for the last part. So let me just copy it down. If there are no errors in first term, the second one will survive. Initial term of G, and I hope, and it gave me this outcome, which is exactly what we got in our calculation. Only thing is that when I get this outcome, it gives me fraction of S and not a polynomial, because we have something in the division. So it considers the fractions of S and gives outcome in the fraction. So for example, when I define this F, here I only had S here. If you see, when I defined F, when I define F, it was, the outcome was element of S. Again, for G also, it was element of S. Okay. But when I did this, it considered it as fraction in S. Okay. So it is like F by G in S. Okay. So to see such elements in S, I have to do this. Sub this element in S. I hope the order matters in this case. So let me just write this for now. This 0, 0. I need to write OO, or to avoid the confusion. Let this above term, let us give it some S. Let us call S or S pair. Okay. So this is my S pair. I want to see this S pair as an element of S. So for that, I need to give this command. S pair, comma S. So now it is element of S. Now, instead of looking S pair as a fraction of S, it now looks it as element in S. Is it clear? It is important because sometimes if I just do this S pair plus x1, now this x1, I wanted to add it as an element, as polynomial in S, and consider this S pair as element of S. But instead of considering it as element of S, it still considered it as element of fraction of S, and see what element it is giving me here, S pair plus x1. Okay. So, and so on. So I hope the things are clear here. When you put something, make sure you get elements correctly. And now, okay. So for now, we will stop and we'll move to next question. Then we will again have to use this S pair, and I will show you like how once you wrote this code, you can use them again and again. Okay. Because every time writing this huge thing is not ideal thing. So we will try to do something of that. So for now, let me just share my next screen. I was okay. So this is how S polynomial or S pair is calculated. And now we will see one example of Buchberger algorithm. We will try to find. We were like, I think Rashid is not here today, but he was asking about the question related to how we can find how to find Grosvenor basis from given generating terms. So we will see in this question, and we will try to find. It is not very I can say calculation heavy example, but this example is just to give an idea like how to do this. So let I be, and we won't be doing everything by hand. We will try to use Macaulay 2 in between, just to be quicker. So ideal generated by, we are taking this x1 square minus 1, comma x1 x3, comma x2 power 4. Okay. Then they are saying that find the, Grobner basis of I with respect to G Revlek, graded reverse lexicographic order or G reverse lexicographic order, whatever you prefer. And K is using Buchberger algorithm. Okay. So what is Buchberger algorithm? It is given as theorem of Buchberger, and it says that G is equal to G1 to Gm contained in I be a generating set. And it has this setup that K from K, R is Kx1 to Xn, K is filled, and this is with some fixed monomial order. Then we consider this G from elements as generating set. G the generating set of I. Then what we have that this generating set G is a Grobner basis of I if and only if for all I not equal to J, the remainder, so what we do, the remainder of S Gi, Gj for remainder. Division by all this G1 to Gi or Gm, or division by elements of G in any order of elements of G, okay, is a 0. So what they say is that we consider that generating set, find all the S polynomials and calculate and see the remainder when we divide that S polynomial. I mean, this division, we do division in multivariable, this, and we see what is the remainder in that case. Okay, so we do that, and that remainder, when it is 0 for all S pairs, that gives us Grobner basis. That is a theorem. And what is Buchberger algorithm? So this algorithm is obtained using this theorem. So what we start with, we again start with generating set of I, generating set, and let us say G, and then for all F not equal to G in G, we compute the remainder of S F comma G by for division by G, again in any order. When I say in any order, the order of the polynomial ring is fixed in any order of elements of G. Why this is important is when you divide some element. For example, let me do this. Okay, x1, x3 square plus x2. Okay, and we divide this by x2 plus 1, x3 plus 1. I don't know whether this will give what I want you to show, but let us try that. If I first multiply it by x2, I get x3 square. Okay. And it becomes x2, x3 plus x2. And when I divide it by this, I get 0 here. Subtraction. Okay. Now similarly, I do this with this x3 plus 1, x2 plus 3. So this is what? So this is f is equal to x3 square into, let me call this f1, f2, f1 plus 0 into f2 plus 0. So this is my remainder r. But if I divide this same polynomial by x2, x3 square plus x3 and I subtract, now my f1 is, or let me do f2, x3 plus x1 and x3 plus 1 and f1 is x2 plus 1. But now I want to divide it by x3 first. So my thing becomes x2, x3 and here I get x2, x3 square plus x2, x3 subtracting, I'm here and I get what? x2, x3 plus x2. Okay. And then this is something. So here I get 0 in first term directly. And now again I have to do this. x2 into, now again first term. So it is x2, x3 plus x2 and I get 0, 0, 0. So this is what now f is x2, x3 plus x2 into f2 plus 0 into f1. Yes, plus 0. So these AI, FIs, and in some cases, R might change. Okay. Depending on what you are using as your multiple and so on. So here, since the element was divisible, it doesn't depend on order. But if it is not divisible, the R changes. Okay. So this example was not good, but I just wanted to show that things change when you change the order using which, I mean, the order of FI to proceed with the division. Okay.
And the first one, the remainder is not.
Sorry?
The first polynomial,
Yes.
the remainder is not 0, ma'am.
Not 0. Okay. What is it? Oh, yeah, it's not 0. It is x2, x3 square. Okay, yeah, you are right. It is x3 square, right? And this is x3 square minus x2. Minus x3 square x2. And now I can divide by either of them. And I mean, it is something, right? It won't be 0. And even, I guess, in this case also, this one is fine. Or even this
Yes.
has any problem.
Oh, ma'am, second is fine, ma'am.
Second is fine, right? So let us try to do things with this here. Let me shift it next page. Or here maybe. And what to do now? We can subtract it using now x3 also. That's not a problem, right? So if I do minus x3 with f2, so it is minus x3 square minus x3. And when I divide it by, I get what? x3 plus x2. And I get some remainder here. I can again divide it by x2 or x3, whatever we like. And maybe x3. Again, it will be x3 and again minus x2. And I will get, so I mean minus x3 minus x2 and plus x2. But reminder, I will get 1 or something like that here, right? Or not? Let me do it clearly, properly. without messing up. Here it is minus x3 plus x3 plus x2. And again, when I multiply by, so minus 1, it is x3 plus 1. And when I subtract, I get x2 minus 1. And again, I get here plus 1. This is with f1, this is with f2, this is with f2, this is with f1. And again, I get x2 plus 1. And I get minus 2 as a remainder. Something like this.
Yes, ma'am.
Okay. So this calculation might have some error. And here we can see here the remainder was 0. But here the remainder is minus 2. There might be, no. Yes, there might be some error. Please go through it. But I mean, when this order I'm talking about here, the order I mean is this order. The order using which we are dividing our polynomial g. Okay, I hope that is clear. So, and what they are saying is doesn't matter using which polynomial I start the division first. Okay, in either cases, my remainder must be 0, unlike this. This still might be 0, please check. Okay. The remainder must be 0 in either case. That's what they mean. So as polynomial, when I divide it by elements from G in any order of choice of G's which we choose, it must be 0. And if they are saying that if H is 0, we repeat for other pair. So we are starting with FG, we are checking F pair, S pair, finding its remainder using all the possible order combinations of elements of G. We check whether the remainder is 0 or not. Once the remainder is 0, great. We proceed, we go ahead with choosing another pair of FG from the generating set and again do the process same. But if this H is not 0, when I say H, I mean the remainder, okay? The remainder H of S polynomial. If the remainder is not 0, we replace G by G union H. Okay? I do this. When the H is not 0, I replace this G by G union H. Now my set has increased. So the original set was F1 to FR. Now my new set is F1 to FR, comma H. Okay? And now again, I find all the S pairs, and then check their remainder with respect to all the possible orders of elements now from F1 to H. Okay, and I see because now there is one extra element there, the possibility of getting zeros. I mean, this extra remainder which we were getting here, now we are adding there. So when I proceed with this is my H, but now I'm adding this H as one of the divisor. And I can do this 1 into H here, I mean 1 with H or minus 2 with S, whatever we want. And I will, now the remainder becomes 0 and so on. So at least for that F comma G where S pair was not leaving the remainder 0, we now at least got 0. Now we proceed with for other pair and see whether all the remainders are 0 or not. And if not, then again we go on adding such. And this stops because every time I add these elements, this F1 to H and so on. Okay. When I add this, I am getting increasing chain of ideas. Okay. And it must stop somewhere. Okay. So this stops and when, okay, stop when all the remainders are 0. Okay. And this stops because ACC of polynomial rings. Okay. this process stops. This is not infinite process that we are keep on adding the elements here, okay? Because the polynomial ring with finite variables, we have that this process stops. So now my elements were, my G was x1 square minus 1, x1, x3, and x2 power 4. Okay, this is my G. Okay, and now I want to find all the possible S pairs of this element. Okay, so what this is like, I first have to find all the S pairs and check which all do not leave the remainder 0. So in order to do that, we have to find, so if I call this F1, F2, F3, I have to find S F1 comma F2, S F1 comma F3, S F2 comma F3, right? Or any other pairs. Note that this is like minus of S F2 comma F1. This is minus of F F3 comma F1. This is minus of S F3 comma F2. Okay, just minus sign changes. But is this okay? These three pairs are there, or any other pair is there. Okay, so we will not manually calculate all these S pairs. We will just use Macaulay tool, and I will show you like how the given formula can be used multiple times. Like we wrote that formula for S pair to calculate one S pair, but we can use that to produce a function which we can revoke anytime in our calculations whenever we want. Okay, let me just share this screen and stop here. So this was my S pair here, right? So which was the code I was showing, and instead of doing this S pair as this, let me just do this and let me define this as a function. This is a function which takes input as a pair and it gives this as output. Okay, and let us see. So now this is function. Okay, so instead of explicitly defining now as f comma g, I can just do this S pair f comma g. Okay, and not only f comma g, let me define h1 is equal to this polynomial. Okay, and this h2 is some other polynomial. Okay, and S pair, P capital. The name must be similar. Okay, I mean, it is case sensitive in that sense. H1, comma, H2, and it gives me this polynomial. And we can see that if I do this H2, comma, H1, it is minus of this term which I was getting here. So we kind of use this S pair to calculate all the terms. So now let me define. So this is now polynomial in, again, 3 variables. So let me define my F1 was x1 square minus 1. F2 is x1 star x3. And F3 is this x2 power 4. Oh, did I make any mistake? Oh yeah, you can't use subscript. I mean this F sub, or this is bad nomenclature. Okay, so F2 was this. So now this S pair of F1 comma F2 is minus x3. Okay, so just we will keep this thing in our mind. S pair of now f1 comma f3 is minus x2 4, and now I want to find S pair of x2 f3, which is 0. Okay, any doubts? Okay, these were the 3 pairs which we wanted to check at least. Okay, no other pair, right? F1 is checked with F2, F1 is checked with F3, F2 is checked with F3, and others are just minus of what we have here. So again, you can see that it is fraction of this. Okay, but that's not a problem for in our case. So this is S pair which we got, and we will for now stop our okay, let me just share my screen here. So there were 3 terms which we were like got. So this was minus x3, this was minus x2 power 4, and this was 0. Okay, so this is what we got, if you remember. So we check the remainder. So when we do the remainder, it is always, I mean, S f1 comma f2 when divided by g, it is minus x3 always. Because see, doesn't matter what you do, you can never get x3 using this. Okay, so x3 is a reminder, non-zero reminder. You can check this. F1 comma f3 divided by g, this is like bad symbol, but I'm using this, which is minus x to 4, it is 0 because this is element from my ideal. And this is anyway 0, so that's not a problem. Okay, so x3 was something which was not giving remainder as a 0 when we were dividing it by elements from G. So what this says that now this is our G dash, which is this G union the H, which is minus x3 in our case. So my now G has become something of element 4. This is like x1 square minus 1, x2 square, sorry, x1, x2, x1, x3, comma, x2 power 4, and x3. Okay, now it contains 4 elements. And now when I try to find again S pairs of all these 4, it will be like S of 1, 2. Let me just write it as F1, F3, S, F1, F4, S, F1, not F2, F3, S, F2, F4, S, F3, F4. And rest are minus of these terms. Okay, so that's not a problem. And we anyway find S, F, G for F not equal to G. So, okay, so that's not a problem. So let us again try to find it using Macaulay tools. We have to switch the screens, but we have no other options. So first thing, when we are doing this, check that we again, we have to find this again and again. So these were only 3 pairs of F1, F2, F3. So I wrote it and write it. I explicitly gave the code for writing S pair, but if you have some ideal with 10 generators, or you are trying to find S polynomial for ideal with 10 generators, like how will you proceed? You can't write like 10 into what? 5 into 9, 45 pairs or something like that, right? That just is not very good. Okay, so for that we can use loops. So Macaulay 2 also supports loops. So let us define this list of polynomials. Okay, which was, let us give f4 to be this my minus x3, which is my, or just x3, doesn't matter. So let us take this L to be list of f1, F2, comma F3, comma F4. So this is this list, okay, of all the elements. And now I will use this list to calculate all the S pairs. So for I from 0 to, so indexing of Macaulay 2 starts with the 0, okay. So when I do this, the size of this list, so hashtag is used to find the size of list. So it has 4 elements. So if I use this, hashtag of OO, so this hash is used to calculate size of the list, okay. So this is my list L, okay. So when I want to find what I can say, I have to give index for I from 0 to, I just use this L minus 1. So because now it is starting from 0, okay. I mean, let me keep this with me for now. For example, L0 is this term, x1 square minus 1. L3 is this term, x3. Okay, so what I do is, for I from 0 to L minus 1, I want to list S pairs, right? But till when? For now J from I2. So when I have I to be 1, I start from, I think, I plus 1. But instead of, I mean, to avoid the extra calculation, it will calculate some more terms, but that's okay. For I from I2, again, hashtag L minus 1. Again, we list S pair of Li, comma Lj. Okay, let us see whether for I from, okay, from 2. So I made mistake from 0 to, here it's correct. Okay, so it gave me 3 lists for 1I, for 2, and so on. Okay, so this is just S pair of other terms. So you can just adjust. So this gave me a few more extra terms. This is like 4, 6 plus 4, 10 terms, which we did not need. But okay, so non-zero terms are this, x3, x2, 4, x4, and so on. Okay, so these were the extra S pairs which we got. And we will see now what is the remainder when we divide it by the new G dash which we have. So extra terms, the non-zero S pairs which we got are this, x3 and minus x2, 4. So again, now my G has x3 in itself. And so I mean, we don't need to calculate even. And this is what? This is anyway element from S. So this x3 along with this term is now giving me the remainder to be 0. Can you understand this? Can you please say yes or no? What I'm saying here is, because I don't want to switch the screen for now, because I would like to check the Buchberger basis right now for these elements. So when we add this H, which was, yes, any doubts?
Ma'am, please explain again, ma'am.
Okay, so let me just go back to screen again. I will share the screen again, and again I will say this. So what I was saying, that even with these new terms with G added, the S pairs, I don't know what for which it was what, but the extra non-zero remainders. So you understood the code. Code was not the problem, right?
Yes, ma'am. Code was clear, ma'am.
Okay, so code was clear. So you were like trying to understand. Okay, so I'm on the right track then. So the non-zero remainders of the non-zero S pairs were what? This minus x3, minus x to power 4, and minus x3, if you remember. These were the only non-zero S pairs. Okay. And now this S pair, these elements, we want to now check whether what is minus x3 divided by now this g dash. Okay. Now what is this? This is 0, right? Because it contains x3 itself. Similarly, this minus x to power 4 into g dash is 0 because x to 4 is also one of the divisor in itself. So that's not a problem. Okay. So both the reminders are getting 0. So anyway, for the 0 S pairs, remainder is anyway 0. That's not a problem. But the non-zero S pairs, we wanted to check whether they give us remainder 0 or not. Okay, this remainder h we wanted to be 0. But now all the S pairs have the remainder 0. So by this theorem, this stops when all the reminders are 0. Okay, so all the reminders are 0 means when we are check. So we checked all the S pairs, right? We check all the FGs and saw the and found the remainders of SFG when divided by G. Okay, when divided by G or G dash as per require, as per possibility, as per what? As per the conditions. And we got them all to be 0, right? And all the reminders were 0. Is this clear? All the reminders were 0. Do you understand that why the reminders are 0? Is it clear, or do you want me to explain it?
Clear,
So
ma'am.
now, okay. So I was doing this, and since so it is like x3, I am dividing by this x1 square minus 1, x1, x3, x2 power 4, and x3 itself. Okay, so it was none of the initial term anyway divide this minus x3. Only possibility is when we divide is this. Okay, so this is minus 1 and we get 0. And this is anyway similar case is with the when I take this a minus x to power 4. The only possibility is minus x to power 4 because no other initial terms divide this x to power 4. So this is minus x to power 4 and 0. So what we do is we start calculating S pair. We see which S pair is non-zero. The moment we get non-zero S pair, we divide it with the elements from G in any order. That order, I hope you understand which order I'm talking about. So any order of these FIs, check the remainder. If the remainder in all the possible orders is a 0, we don't do anything. But when we get the remainder to be non-zero, for example, in this case, when I first divided by x3 in first case, in first part, when we check the S pairs, x3, when I was dividing by these three terms, x1 square minus 1, x1, x3, x2 power 4, the remainder was x3 itself. It was not 0. Okay? Because nothing could divide x3 here. So when I calculate, so x3 was 0 fi summation 0 fi plus x3. So the remainder in any order, remainder in any order was x3. So this is non-zero. So we added it here in my G. And now I again calculate all the S pair, including this H. And now when we get non-zero S pair, I then divided with this new g dash, which has h in it. So since we had this h added here, which was giving me non-zero divisor earlier, I'm getting 0 now here. And that's when we stop, right? When all the remainders are 0, when we divide it by elements of G. Is it okay?
Yes, ma'am. Clear, ma'am.
Okay, clear, na? Great. So now we got something, right? I mean, we got this, that my Grosvenor basis must be this 4-element thing. Okay, so this is what we got. Now let us check whether this is actually the case, because we did the calculations by ourselves. We found these divisors using our things. I mean, of course, we used as Macaulay 2 to calculate S polynomials, but we did check the division by ourselves. And so let us see. So let I be this. Let me stop this. So let I be this ideal. So remember this F1, I'm just writing this. F2, F3 are these elements, right? F1, F2, F3 are these elements. So let us define this I. So this is what my G was initially. So I'm defining this ideal by F2, F1, F2, F3. So this is my ideal. And let us see Jane's GB of I. Oh, what order is defined on S? It's, what is the ideal? Let me check. X1, X3, X2 power 4. With respect to F1 is X3. So instead of writing X1, X3, it gave me X3. Because X3 is anyway multiple of X1, X3. So when we write, when we give this, what I say, when we do this calculation of Grosvenor basis in Macaulay 2, it gives me reduced Grosvenor basis. So what is reduced Grosvenor basis? It removes all the unnecessary or all the unnecessary elements from the Grosvenor basis, because the moment I have xt here, it removed this x1, x3, and it only kept this x3 here. Okay, so this is reduced Grosvenor basis when we calculate it in Macaulay 2, and which is not bad, because what we got is x1 square minus 1 is there, x2 power 4 is there, and x1, x3, which is anyway multiple of x3. So in reduced Grosvenor basis, we remove all the redundant polynomials, that is the polynomials which are multiple of other polynomials. Okay, and so that's what we got here. So Jane's DB gave, so if I help Jane's DB, let us see. Okay, help GB. Okay, so it gives me Grosvenor basis, and let us see what it does. Input and output is Grosvenor basis computation, and it gives C. Auto reduced Grosvenor basis are obtained by applying generators. Okay, so when we did that, when we do this Jane's GB, so when I do GBI, it is Grosvenor basis, and so it calculated everything and so on. So that's why that x1, x3 element was not there, which is there in our Grosvenor basis. So our Grosvenor basis is a Grosvenor basis, but what Macaulay 2 gave was a reduced Grosvenor basis. Okay, any doubt here that what we did was not wrong, but the Macaulay 2 gives us reduced Grosvenor basis, and that's why we saw this. Any doubts? So you can always use this help term and put the name of code which you want to check and see what Macaulay 2 gives. It gives the entire information. GB is it computes Grosvenor basis, what kind of algorithm it does, what it use, how it is used, and so on. Okay, so I hope there are no doubts, and the calculation we did was completely correct, because anyway after adding x3, the elements giving as polynomials to be non-zero, and what 0 and non-zero, wherever it was non-zero, all the remainders when we were dividing it by this new list were 0. So our calculations were actually correct. And to keep this in mind, when you calculate Grosvenor basis in Macaulay 2, it gives reduced Grosvenor basis. So again, I will go back to our screen. So let us check this next question. Okay, it will take some time, but we will do this. Okay. Question, what this question number is, whatever maybe it is. I don't know whether I'm following correct question numbers, but let us consider to be question 9. And question 9 is that what is the kernel of the ring map C x y z to Px, where f of x y z goes to f of x, comma x square plus 1 and x cube plus 1, and they have these options that f of x minus x square minus 1, comma x minus x cube minus 1, b is y minus x2 square minus 1, z minus x cube minus 1, and c is x comma x square plus 1 comma x cube plus 1, and d is none of the above, or yeah. So we want to find kernel of this map. So again, we have this 3 possibilities. So we see which one suits the best. Definitely, this one doesn't give any hope for to be kernel, because in this case, f of x, they are saying that in part C or in option C, they are saying that x belongs to kernel of, let us call this map phi, kernel of phi, but that's not the case, because f of x is f of x, right? Which need not be 0, because I can simply consider this polynomial f of x plus 1, and it is what? P of x plus 1, then it is what? X plus 1, which is definitely non-zero. Okay, so this definitely C is not the option. Now, these two are still better candidates. So let us check for A. Okay, so what A has? So it says that this belongs to kernel. So what they are saying that we have to check whether this belongs to kernel of phi or not. Okay, so when I apply phi to this x square minus 1, it is what? X minus x square minus 1, right? Because there is no y term here. X anyway goes to x. So it remains as it is, and which is definitely non-zero. So this is also not my kernel. Okay, so now the B part. So B has this term y minus x square minus 1. Okay, we have to check whether this belongs to kernel of phi. And let us calculate phi of this y minus x square minus 1. But what is this? This is phi of y minus phi of x square plus 1, right? Phi of x square plus 1 is phi of x square plus 1. That's not a problem because x anyway goes to x. But where does y go? Y go to x square plus 1 here, right, under phi. And now this is 0. So definitely this element belongs to this kernel phi. Okay. Similarly, when I do this x cube minus 1, this is phi of z minus phi of x cube plus 1. And phi of z is this, and minus this goes as it is, which is again 0, and that's why this belongs to kernel phi. But again, whatever this ideal here is, this ideal we can only say that it belongs to the kernel of phi. But now we want to check whether this is equal or not. So do you remember any result of this kind from the lectures? Okay, so let us write this remark. This is done in the lectures, that if R is this polynomial ring x1 to xn, okay, and S is this polynomial in some other variables. Okay, the variables are different now, y1 to ym, if I have, and if I define this ring homomorphism from phi from R to S, such that the xi goes to gi, with gi is some polynomial in S. It doesn't matter. It is just some polynomial in S. Okay. Then we do this. We define this phi tilde from T to K from y1 to ym and x1 to xn to S. Okay. Then again I define this xi anyway goes to gi, because anyway our original elements must go to whatever we wanted, and now we have added this yi's, right? So yi we send to yi, because yi's are anyway variables from S. So yi is anyway going to yi. So therefore what we have is that kernel of phi tilde is actually, kernel of phi is actually kernel of phi tilde intersection R. So kernel of phi tilde is in bigger ring. Kernel of phi tilde is in this ring. Kernel of phi tilde is in this ring T. Okay. But kernel of phi is in our original ring R, which is contained in T. Okay. So they say that this kernel of phi is intersection of kernel of this new map phi tilde intersection R. But why this phi tilde is so important? Because they say that this phi tilde is nothing but x1 minus g1 up to xn minus gn. Okay. So this is, I mean, straightforward. We have information about a kernel of phi tilde, and using this, we find this kernel of phi. Okay, so that's why using this, in our case, what we have, our original map, I can consider this C from here to Cx, such that y goes to x square plus 1, z goes to x cube plus 1, which is my phi, and my phi tilde is this map x comma y comma z going to Cx. Okay, and now this map is such that this y goes to this, z goes to this as we have, and now my x going to x. So it looks like this map, right? And in this case, what is the kernel? It is all this xi minus gi terms. Okay, so therefore this kernel of phi tilde, which is actually the original map which we are working on, is this y minus x square minus 1, I mean x square plus 1, which becomes x square minus 1, minus z minus x cube plus 1. So any doubts here? Here it should be minus. So any doubts? We just use this result from our lecture, that this is the kernel of this. Okay. So I hope this is clear. So this is actually the correct option which we have here. Okay. And this is one last question I would like to, because we have also learned about elimination, right? In our lectures. So we will do that also. Just a second, let me check. If we can do that. Okay, let us do this question about presentation. It will take some time, but we will do. Question, I guess this is question 10. It is not actually question 10, but okay. So write down. So this is question from our notes, the non-graded assignment. I request you all to please go through the non-graded assignments, because it has many extra definitions and questions which are like very important to go through, because those questions will clear our concepts related to what we are doing here of the ideal x comma y square in k x comma y. Okay, and we have learned about presentation matrix already. So what is presentation matrix? So if M and R module, I hope you all know what is module. And if M is finitely generated, of course, as a R module. And then kernel of this Rn to M map, this surjective map. So this is also there. So if a module is finitely generated, there exists integer n such that we have this surjective map from Rn to M. And we say that this kernel is also finitely generated. I mean, not say that. We are assuming that this kernel is also finitely generated as R module. Then, so they say that we can say that M can be presentable when, I mean, M has a presentation matrix only if M is finitely generated and this kernel of this map from Rn to M is also finitely generated. Then only we can say that M is finitely presented module. And what is this finite presentation is? So when I have this kernel F from this Rn to M map, so I'm talking about M, this is surjective map. And again, since kernel F is also finitely generated, there exists again some surjective map from Rm to Rn. And the composition here, we call this phi. And this phi is a map from Rm to Rn. So we can look at it as linear maps, which can have matrix representation. So this phi from Rm to Rn is our linear map. And so phi can be represented as a matrix. And this matrix is called presentation matrix of M. Okay. So this is now presentation matrix of M. Okay. So because this Rn, which we are factoring through this kernel and everything, they are all obtained from the M. Okay. From our original matrix M. So how to do this? Okay. How to calculate this? So let us do one quick example. So let us take this ideal 2 in Z. So this is also given example in our, in the question, a non-graded assignment. So Z is Z1 to 2, okay? So 2, I can, the ideal generated by 2, I can look at it as one copy of Z, where 1 is going to 2 and so on. So each element I have this. So this ideal 2 in Z is one copy of Z. Okay, so where 1 is going to 2. So these are linear maps. These are not ring homomorphism. These are like module homomorphisms. So the difference, please, understand the difference between module map and the ring map. Okay. And this is now Z0. And so this is injective map. So kernel is anyway 0 of this map. Okay, so this representation matrix is 0. It has nothing because this is 0 to this, and so 0 is what? 0 copy of Z. So everything is 0 here. But instead of looking at this ideal generated by 2 as ideal generated by 2 comma 4, if I take this as ideal generated by 2 comma 4, 2 copies, this is redundant actually. But I want to look at it as ideal generated by 2 comma 4. Then I have this Z2. And what is kernel of this map now? If I take 2 and 4, then it is, if I consider this as E1 and E2, this is 2E1 minus E2, right? I am now looking at ideal generated by 2 as 2 copies of Z2. You can do that since we are in modules. Okay. And when I look at it like this, I get this now Z1, because this is now ideal generated by one element. So this has one copy of Z. Okay, so this is Z1 to 1. And so in that case, what is this? This is E1 going to 2 and E2 going to -1. So the representation matrix is this 2 cross 1 matrix. Okay, so here it is E1 going to 2, E2 going to 4. Okay, so Z is generated by E1 comma E2. Is it clear? So for this, at least this is element. We can see that exactly this is the presentation matrix. We will try to do this in Macaulay in quickly in next few minutes. But now I want to do for this, right? This is x2 square, xy, y square. Okay. So this is contained in kxy. Okay, which is R1. But now this is ideal generated by 3 elements. So this has now 3 copies of R. So my original M is R3 to this x square, xy, y square. It has 3 copies such that E1 goes to x square, E2 goes to xy, E3 goes to y square. Okay, and what is kernel of this map? Can you all guess? So note that when I multiply E1 by y and E2 by x, I get x square by y square x. Okay, so I can have one element to be this y minus x is 0, right? Similarly, when I multiply this by x and this by y, I get what? X is 0, y minus x. Similarly, this is x square into y square, right? I can do this by, I multiply this by x square, this by y square. This by y square, this by x square, and do this. But you can see that this is redundant element. You can obtain it from here. Multiply this first element by y, this by x, and when you subtract, you exactly get this element. So it is generated by only 2 elements. So this kernel of this inclusion map here is generated by only these elements. I know I'm going quick because we are over time. But now this is this is ideal generated by 2 elements. So it will have 2 copies of R. Okay. So this is R2 here, where E1 is going to, suppose I call this U1, this is U2, and E2 going to U2. Then this presentation matrix is exactly this element, y minus x 0, and this 0, y minus x. Okay, and this is my presentation matrix of this x comma y square. Okay, and you can quickly define, I mean, this is like last, which I will be sharing for today. And we will quickly see that this is exactly actually the presentation matrix. Okay, so we can define this. What is my polynomial ring? So let us keep this polynomial ring q x comma y. Okay, and let us try to define this. So f is map from, so there are multiple ways you can try to do this, from R1 to R3. And now since these are module maps, we have to define them as a matrix. Okay, so that's why this double what I can say, these double brackets, unlike small, it must be capital. So this is now map from R3 to R1, and it considers it as a matrix. And when I try to find this kernel of f, which is exactly what we have, and this is what we got. Okay, this is exactly what we got. Okay, but instead of this, there is also one other way to define or directly calculate a kernel. So if I define this M to be this matrix, okay, and N to be image of this matrix. This is just for it to consider it as an R module instead of just some matrix. So when I do this, it takes image of this matrix. And when I do this presentation of this N, it gives me this exact matrix which we have here. Okay, so this is how we can do. And just so you know, this you can do for example, if I do instead of this, if I do this for z, 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 z power 1, and if I do this only, that 2, okay, and I find kernel of this map f, this is okay, image is just this 0, okay, but if I do this, f is equal to map, I know we are over time, but still this is z, z, z power 1 to z square. Okay, we are going from z to z. We went from where to where? Z to z square. Z to z square with matrix 2 comma 4. Okay, and when I find kernel of f now, it gives me this matrix 2 comma minus 1. And you can clearly do this also for this matrix also. If I define matrix 2 comma 4, 2 comma 4, and I do this just presentation image, this matrix which defined earlier, it gives me this. But the moment I define this as matrix just 2 and try to find image, it gives me this 0 matrix here. So I hope this is clear, the presentation matrix topic which was covered in the lecture. Any doubts here? Any doubts, please let me know. Otherwise, we can stop. Any doubts? I hope the concept of presentation matrix is clear and how we can calculate it. Okay,
Yes.
no
Yeah.
doubts. Okay, great then. Yeah. If you have any doubt, please. Otherwise, we can end the meeting for today. Okay, I guess no doubt. So thank you. We will meet next week.